All right. So today we're going to talk about composite functions. Basically, these functions depend on another function, and it's formed when we have maybe two functions and one of them gets subbed into the other one. So here's the notation that you're going to see. This is read f composite g at x. This is not fog. Okay, this little composite symbol is not an O. It's like it's almost like how you write multiplication, but it's like a hollow little dot. And basically what this means is that we will take f and sub in g at x inside wherever we have an f, or wherever we have an x, oh my goodness, wherever we have an x in f at x. All right, so let's take a look here. So for the first one, we're using the notation that I introduced to you above. So that means that we're taking g at x and we're plugging it inside the x's for f at x. So here's my g at x function. We see that in our equation, it's equal to x minus 2. So we're actually going to evaluate f at x minus 2. Okay, so just as a reminder, we've talked about this, I think, a couple times, like when we talked about Newton quotient and stuff like that. But if I were to evaluate, let's say, don't write this, but if I wanted to evaluate f at 2, can you guys tell me what I would do in this scenario where f at x is x squared minus 1? How would I evaluate f at 2? What do we do? Alexandra? Yeah, we sub in 2 for x wherever we see an x, right? So if I want to evaluate f at x minus 2, I am going to sub in x minus 2 wherever I see an x in f at x, right? So in this spot for x, we're actually going to replace that with x minus 2. So I will have x minus 2 squared minus 1. Okay, and then perhaps we could get this maybe into factored form. So if we expanded this guy out, two things that multiply to 3 and add to negative 4 would be negative 3 and negative 1. Okay, so factored form is typically simplest form for these guys. Actually, both of these forms here are going to help us graph below because one's vertex form and one's factored form, so that will be helpful. Okay, now if we do the opposite, f or g composite f at x, what we're actually doing is plugging in f at x inside of g at x. So I want to take my f at x function, which is x squared minus 1, and I want to take all the x's in g at x and I'm going to sub inside the x of g at x, x squared minus 1. That's what this is telling me to do. So it's going to be x squared minus 1 minus 2, and that gives us x squared minus 3. Can't really go any further with this. It looks similar to a difference of squares, but 3 is not a perfect square, so this is about as far as we can go. All right, and then this is asking us to sub in g at x into g inverse of x. So we have to remind ourselves of how to find an inverse, right, Claire? Yes. And I think this one's not too bad. What's the opposite of subtracting 2 from x? Adding 2, yes. So g inverse of x in this case is just x plus 2. So what I want to do is in g inverse, I want to plug in x minus 2, in for the x there. So in g inverse, I'm going to substitute x minus 2. And the result here is that we get x. Okay? This is always, always, always going to happen if I plug a function into its inverse. The definition of the inverse is that it does opposite operations in the opposite order. So if my function that is the inverse does the opposite operations in the opposite order of f at x, if I sub in f at x into f inverse of x or vice versa, I'm going to be left with just x, right? Because all the operations will undo each other. That's what ends up happening. So all the time you'll see if I plug in a function into its own inverse or vice versa, I'll get x. Okay? All right, so we're asked to graph these guys below. So let's graph this one to start. How can I graph this? X minus 3, x minus 1. What are some things we know about this function? How about the x-intercepts? What are my x-intercepts? Liam?
3, 1, 3, 0.
Yeah, great. Anyone know my y-intercept? I can get that from, yeah, how'd you get that? Yeah, it's the constant, or you can just plug in 0 for x, so it's 0, 3. Anyone know the vertex of this quadratic? We have vertex form up here. Not 3, 1. Liam? Close? 2, negative 1, yes. This is like the h and the k value of the vertex where we switch the h, if you guys remember. Okay, so I think that's enough. We can plot these. And this will be reflected on the other side, that y-intercept there. And we can graph. Okay, and I'm just assuming here that my scale is going by ones on both the x and y axis. Oh, what did I do wrong here? Oh yes, this is, sorry guys. I made a mistake here. Just checking to see if you're awake, you know. This is 2, negative 1. That makes much more sense because it should be going up like this. Sorry. You can do whatever you want, Jeremy. You go for it. All right. Second function. Can I find the x-intercepts even if I can't factor it? Could I do that? Where is x squared minus 3 equal to 0? Well, if I try to solve for this, I'm going to get 3. And then I will take the positive and negative square root of 3. So those are the two x-intercepts. If we calculate the square root of 3, can someone give us an approximate value of that so we can plot it? What's the square root of 3? 1.7-ish, we'll say. Yeah. So here and here. And the y-intercept for this also happens to be the vertex. It can be found at 0, 3. And I'm just using, or sorry, negative 3. And I'm just using the constant for my function here. So that is actually going to be right down here. And h at x equals x. So I set my function equal to 0. So I'm setting the y of the function equal to 0 and solving for the x that makes that happen. It's kind of like what we're doing when we factor, right? Okay, and then think of this. So this is the function h at x equals x. So this is that diagonal line. It's probably the first line that you learned about in grade 9. It's just where all the x's and y's are equal. So 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and so on. So it's just that diagonal line, and that's also the line that inverses are reflected over. So here's our line. Okay, any questions on anything here that I can clarify? No? We're all good? Any confusion as to where any points came from, anything like that? We're good? Okay, can I scroll? Everyone's good? Okay. All right. R composite Q at 2. So what I want to evaluate is R, where Q equals 2. So firstly, if we find where Q equals 2, I might just even do that off to the side. I can just enter in 2 for the function Q, and I get 1/4. You can also do it inside this if you want. But now I know that I want to evaluate R at 1/4. Okay, and then I'm just going to put that into my function. So 1/4 squared plus 5 times 1/4 minus 1. And I'm just going to find a common denominator here. This is 5 over 4, so when I multiply that by 4, it'll be 20 over 16. And this is 16 over 16. And I think we get 5 over 16. Okay, and then similarly for this guy, we're going to evaluate Q where R equals -3. So this is Q at R at -3. So if you want, off to the side, you can just evaluate R at -3. So we're plugging in -3 for all the x's here. Okay, so that tells us we want to evaluate Q at -7. So we're just going to plug that in for our x value. And we get -1/5. Sorry, what do we say?
The A,
Mm-hmm.
like if R and R equals Q, whatever.
Yep.
If Q x equals 1 over x plus 2, how do you get 1 over 4?
Because I'm evaluating Q at 2. That's what this tells me, right? So I just did that off to the side here, and I'm plugging in 2 for x, right? So I get 1 over 2 plus 2. Make sense? Okay. So far, so good? Did I do all my math right? I don't know, man. Am I good, Olivia? You said no?
No, yeah.
Oh, okay. All right. Can I scroll here? May I? Okay. So composite functions are really good if you have a relationship between two things. So when we talk about like actual applications of these things, there are things in the world that are directly correlated with one another, right? So a really good example is kind of like predator and prey relationships. So if we talk about like the number of antelope in a wildlife reserve, as a function of time in t years, it could be modeled by the function a at t equals 40 cos t plus 80. And then the number of lions in the same reserve can be modeled by the function L at t equals 0.5 a at t minus 2. So we're going to find the full equation for L at t. Start with that. So we're going to kind of have to work our way from the inside out. So I want to first just evaluate what is a at t minus 2. I'm just going to do that up here. So that means if I evaluate a at t minus 2, what is that telling me to do in the right side of my function for a at t? Not set it to 0. So I have to sub in t minus 2 where I see a t in my equation, right? So it will become 40 cos t minus 2 plus 80. So whatever you see here gets subbed in for, if that's getting subbed in for t, then I must replace this t with that as well. That's what it's telling me to do. Okay, so here's the function a at t minus 2. That actually goes in for this right here. So it's going to be 0.25 times 40 cos t minus 2 plus 80. And I think we can just simplify this by bringing in our 0.25 in for both of these terms here. So we'll get 10 cos t minus 2 plus 20. All right, so while you guys finish copying that, I'm just going to pull up a graph here. So that we can see what's happening with these two functions. Oh, that's not what I wanted. Okay, so here we go. So the red function here is representing the number of antelope over time. So I've graphed 10 years here, or you can see about 11 years. And the blue graph at the bottom is the lions. Okay, so talk to me about why the number of lions would be less than the number of antelope. First, let's discuss, yep.
So the lions can't have more than what they eat, right? So their numbers should be lower so they can sustain themselves.
Right, so of course the way the food chain is going to work is that if I have like tons of lions and like not enough antelope, those lions are not going to survive. So there's less prey, or sorry, there's more prey than there are predators. So the number of lions needs to be significantly less than the number of antelopes. Okay, now let's talk about what's happening with the way that these functions are related. Liam, what do you think?
So every time that the population of the antelopes moves up, the lion also moves up to the point where the lions eat a bunch of the antelopes and the antelope population goes down. Then the lions can't sustain themselves in the whole population and the population dims.
Okay, so here, about here, the population of lions reaches a maximum, right? And we'll see shortly after that the population of the antelopes is reaching a minimum shortly after, because there's more lions, right? So if more of those lions are eating more antelope, they need more antelopes to sustain them, and then eventually those antelope reach such a minimum that the lions can't find any food. So then our lion population begins to decrease, right? Because there's not enough food to sustain all of them. That gives the antelope a little bit of time to recuperate, so we'll see their population rising. Eventually that population of lions reaches a minimum, but the population of antelope is recuperating, so eventually those lions will also start to grow, okay? And then the pattern is cyclical. So that's kind of what's happening with our lion and antelope population. So you guys can create a little sketch of this. I will do it with you guys so that it's not, so I'm not just copying. It's like a, I guess, no, they're like a deer type thing.
This is sad. I'm sorry, but this is just sad. You don't know what an antelope is?
No,
Have you watched Lion King?
I actually haven't.
Just search
Really?
The cartoon one or the, I know. I
haven't
really
watched
have
Lion.
zero childhood.
Just search up antelope.
Yeah.
Sure.
Don't even I don't hardly watch the Lion King, but even I know what an antelope is. Like, what are your pennies in this one?
Sorry, I don't study the wildlife.
Oh my god.
Yeah, it's kind of like the
This generation.
safari version of like a deer or something like that. Yeah.
I've got to give that up.
Yeah, now you
Oh,
know.
yeah.
You learn something new every day. If you weren't in this class, you'd never know what an antelope was.
Yeah.
How did you never watch the Lion King?
Guys, I should have said yes. I think of that. No, I don't know.
You need to watch it.
I know. I need to now, apparently.
It's basically sport penguin
All right. So how can we describe this? We'll say
Cold skin analysis.
as the population, I'm just going to do this for population, of lions grows, they eat more antelope. E on the end of that? Yeah. Causing their population to decrease. Eventually, there are not enough antelope to sustain the lion population. Okay, so the population of lions is going to decrease. This gives time for the population of antelopes to regenerate, or for more antelope to survive. giving more food to the lion population, allowing it to eventually grow, and the cycle repeats. All right, so all this to say that those two things are directly related, and that's why our population of lions was actually dependent on this population of antelopes, right? But the time is a little bit delayed. That's why we have t-2 here, because the population of lions is slightly kind of offset from the population of antelope, because they're directly affected by one another, but not immediately, right? It's just slightly delayed. So those things will kind of reach maximums and minimums at slightly different times based on what's going on with their populations, right?